Then I will start my lecture. Today is lecture 12. Today's subject is patch antenna and array antenna. First of all, I will explain patch antenna. This figure shows the structure of a patch antenna. Patch antenna composed of three parts: patch plate and substrate and ground plane, and someplace feeding point is placed. From behind, the patch antenna is fed by a coaxial cable. So the radiation pattern performed in front of the patch. So as we understand from this figure, this structure is very rather simple, and the feature is a low profile, very thin structure, and the size may be moderate, and the gain is also moderate. This gain is larger than the wire antenna. So this moderate gain is selected for many communication systems, and fabrication is rather easier. We can fabricate by large substrate plate. Substrate plate has two metallic plate, ground plane, and opposite side one plate. So by etching, remove surrounding area, then we can achieve this structure very conveniently. So this etching process is suitable for mass production and cost can be reduced, very cheap cost. So from these features, patch antenna is used in many applications. For example, smartphone antenna. In your smartphone, this type of antenna is equipped, and GPS antenna. And sometimes this is patch antenna itself. However, patch antenna also use radiation element of array antenna. So for the mobile base station antenna, this patch antenna is used. Or another reflector antenna feed structure. This patch antenna is very widely used for many applications. So next, I will explain the operation principle. The most typical structure is rectangular patch. Another shape is a circular patch. This circular and rectangular is name is given for the shape. This is rectangular shape, and this is circular shape. The electromagnetic principle is this: the patch plate and the ground plate. There is this two plate perform electromagnetic resonator. So in the rectangular patch like this, a resonator is for the circular patch also. The resonance happens between the patch plate and the ground plate. So resonator has a very special electric field like this. The opening part of this resonator, the electric field become highest, and coming to the center, the electric field reduce, and at the center, electric field becomes zero, and from here to the right side, the orientation of the electric field become inverse. So this electric field is to the upper direction. From the center, the electric field becomes the lower direction. And the electric field strength become highest at the opening place. So this is the fundamental resonant mode. So from this distribution, we can understand this length is half wavelength of the inside wavelength. This wavelength in the this substrate is calculated by lambda 0 is free space wavelength divided by root epsilon r. Here, root epsilon r is a permittivity of the substrate. So permittivity of 4, in the case of permittivity 4, the wavelength in the substrate become, this is a root 4. So the inside wavelengths become half of the free space wavelength. So like this, this fundamental mode become like this. This distribution is called mirror symmetry. Around this center point, left side and right side come mirror symmetry. So this is the fundamental understanding of the patch antenna. In the case of the circular patch, the distribution is almost the same. So by using this special electric field distribution, input impedance adjustment may be achieved very convenient. This shows the input point. Here, this is the feed cable. So usually for the feed cable, coaxial cable is used. This is the inner inner wire of the coaxial cable. The inner wire is attached to the patch plate, and here the feeding is given at this point. So here we can see the input at this point. The input impedance is the ratio divided by voltage by current, this voltage. And this voltage is calculated by the distance and the E field. So here, current is given. So at this point, electric field is 0. This is a symmetric point. So the electric field becomes 0. So this equation, if E equals 0, Z in becomes 0. So at the center point, we feed at the center point, the input impedance becomes 0. At the most, the opening plate, if we feed, then the electric field become more large. So the input resistance impedance become around 127 ohm. So between impedance 0 and the highest, between these 2 points, there is a 50 ohm point. So this point become around 1/3 from the opening point. So the impedance matching of this antenna is rather easy. To selecting the adequate feeding point, we can adjust 50 ohm input resistance. So the feature of this antenna, patch size is determined. Half wavelength of inside the substrate, and impedance matching is very easy by selecting the adequate position. And another one more, this is patch length, and width of the patch is also. The important thing is this length is half wavelength. However, the width have a rather pre-selection. However, generally the width is selected almost equal to the length. Square patch is generally used. So this is the principle of a patch antenna. Remember, size is determined by half wavelength, and the distribution is mirror symmetry, and by the special distribution, matching is very easy. So next, the radiation pattern. So this is L, and this is W. So radiation happens from here. The electric field cancel out to the far field. This plus, this minus. So from this opening, no radiation happens. However, another side, the electric field becomes the same direction. So this side can contribute to the radiation. So this side and the opposite side, the This red line shows H field. So H field, electric field is this down and this side up. However, magnetic field becomes the same direction. So from this magnetic field, the radiation is achieved. So this magnetic field, two magnetic field become radiation source. So only one radiation source, it becomes almost uniform radiation. However, by adding two radiator, the radiation become concentrate, and in the source direction, it also the radiation is performed, not uniform. So by this mechanism, two radiator produce directional radiation, and in the source direction also some limited radiation pattern. So totally, the radiation pattern become like a pencil beam to the radiation direction. So this shape produce antenna gain around 7 dBi. So previously, in the case of dipole antenna, the gain was 2.15 dBi. So compared to dipole is this one. Only one radiator, the antenna gain become almost 2 dBi. However, the two radiation exist, then the antenna gain is increased, and finally it become around 7 dBi. So this is more detailed radiation pattern. Y Z plane. This is contribution of two, and XZ plane is this is direction of radiator, a little bit wider. However, around the center part, almost the same radiation characteristic. So I explained a moderate gain. So this gain is larger than the dipole. So for a little bit higher gain is necessary for the smartphone. This can be used as a receiving antenna. And so the principle and the antenna radiation pattern can be understood. So next, by using the mirror symmetry, this is this left side and right side. The electric field become inverse. This mirror symmetry can be achieved if the metallic wall change. From here, the this wall show as if the behind the wall there is a inverse electric field. So this original structure and the wall in the center. This is the same electric field distribution produced. So only the half size can be produced, operate in the same electric field. So we can select some adequate point to achieve 50 ohm input resistance. So this shows like this. The full size is half wavelength, and at the center we put the metallic wall. This can perform from the previous structure at the same of the this full size patch. So this is by this mirror symmetry performance, we can reduce the size to half. And more, this metallic wall size can be reduced. Then more small size can be achieved. This is called inverted F antenna. From the cross-sectional view, this metallic plate is here, and the feed is someplace. So this shape seems alphabet F. So this is called inverted F antenna. So like this, by using metallic wall, the antenna size can be reduced more and more. So next, bandwidth. Before bandwidth, some touch plate thickness. In the previous discussion, if we use the metallic wire or metallic plate, the thickness become very important. I already explained the skin depth, this value. This is the area current flow strongly. So this metal thickness should be larger than this skin depth. Generally, thickness should be 2 times of skin depth. So if frequency become higher, omega is 2 pi f, frequency become higher, so delta become I think so I will check once more. higher frequency, delta becomes smaller, and low frequency, delta becomes large. So I will check once more this part. However, the thickness should be 2 times larger than the index. So this is one condition that should be considered, the thickness of a patch plate. So this is some consideration for selecting the patch thickness. And next is bandwidth. So bandwidth is determined by the Q factor. Q factor is this definition, stored power divided by lost power. Lost power in this case is ohmic loss and the radiation. So radiation happens outside and under the inside the patch, some energy stored. So in the case, in this patch antenna, this is resonator. So the stored energy is considerably large by the radiation. So Q factor becomes almost larger than 100. So the bandwidth of a patch antenna, bandwidth is proportional to the inverse of Q. So this is almost larger than 100. So bandwidth becomes around 1%. So practical bandwidth is almost 3 to 5%. This bandwidth is rather narrow compared to the dipole antenna. And so bandwidth is relating to Q factor. Q is Q factor is how much resonance is strong. And if this patch and the ground plane distance is small, then the resonance becomes more strong. So Q become higher. So the distance the distance patch and the ground plane becomes smaller. Then high Q, so low bandwidth. So the very thin patch antenna has small bandwidth. However, the distance is increased, more space from the front plane, then we can increase the bandwidth. So this relation can be easily understood. So the bandwidth description is determined how much resonance is strong. If resonance strong, Q become higher. So beam becomes small. Are you okay?
Okay, Sensei.
Okay, the principal resonator. This resonator, we can understand the value of bandwidth. So, yeah, additionally, some small size technique. Already, I explained the mirror symmetry by putting the short plate here. First, reduce half size and the short plate becomes smaller, then it becomes more smaller. So that is inverted. And if we would like to reduce the size more, we can put cutting on the patch plate. Then we can reduce more. Maybe in your smartphone, if you can inside that may be this shape, can see. This is a patch antenna case, small antenna technology. In the dipole, wire antenna, the straight line can be like this rectangular shaping or coil shape. This too can be reduced antenna size. So sometimes this antenna height can be reduced. This horizontal line is the antenna height. Half height is dipole and both are 1/10 and very small. So this can be achieved by this meander or helical structure. However, by reducing the length like this equation, the dipole and the small loop resistance become reduced. So when reducing size, input resistance become very small. In the case of like this, less than 1/10, the this ohmic resistance situation is so the patch antenna is now an array antenna like this. There is a category linear array and planar array. This is one-dimensional array, and planar is two-dimensional array antenna. Array is arranging radiation element. Linear is in the linear direction. Right? The performance, two types of performance is exist. Radiation perpendicular normal to this linear line, it is called broadside to the rectangle is broadside array. And in the linear array, on the array axis direction radiation, that can be possible. So this is called end fire. This is end direction of array arrangement. So radiation performance is two types: broadside radiation and end fire radiation. Other typical end fire array TV receiving antenna called Yagi array. That is very famous, and you know this array very well. This is TV receiving antenna. So this is a reflector, this is a feed, and this is director. Director should be more number. So radiation happens to this direction. So this is very popular for TV receiving antenna. And develop of this antenna is Yagi Uda. They are Japanese researchers. So from the developed person name is used for this array antenna. So for this array antenna, there is very famous story. In the World War II, Japanese researcher Yagi, Dr. Yagi and Uda developed this array antenna. However, in Japan, this antenna is not so interesting. However, in the United States, this array is very become famous, and they use this antenna for radar, airborne radar system, or atomic bomb. This array is used. So when Japanese army occupied Singapore, they find this antenna. So they find out this name. They called this Yaji Uda. So they cannot understand what is antenna. However, in later, this is a Japanese inventor name. So the Japanese army surprised very much and understand the United States very much interested in new technology. This story is very famous for the antenna designer. So this is one practical application and fire. However, mostly high gain antenna, this broadside array is used in the mobile base station. This broadside array is employed. So another is this planar. This linear is placed in 2 dimensions. This is a very high gain antenna. So in many applications, this is used. So as a fundamental understanding, I will discuss the performance of broadside array antenna. This array is this is the mobile base station case. The array element is placed in the vertical plane, and the radiation becomes in the horizontal. So the radiation is constantly in the normal direction. So this is operation in broadside array. So fundamentally, this circle show the array element, radiation element, and radiation element is placed by the separation D. So total number of radiator is N, and the total length is, in this case, N minus 1. So radiation can be obtained by adding all the elements to the radiation direction. If the first radiator, this distance is expressed by R, then the contribution to the radiation direction becomes V0 is this excitation coefficient, V0 multiply exponential minus JKR. So next radiator is excitation V1 and exponential minus JK R minus D cosine theta. D cosine theta is difference of this one. So second radiator, the distance becomes smaller by this value, D cosine theta. And third is this 2 times shorter. So that is shown here. So by calculating all, adding all the elements, it is expressed the minus JKR, the equal in all equation is put outside, then the relating to the position part is expressed by this one, V0 plus V1E JK D cosine. This is 2 times JK cosine like this. So this is expressed by H theta. And here for the convenience, KD cosine theta is put by phi. Then A expression becomes like this. V0, the first element excitation, and next V1 exponential J5, and next V2 exponential 2 times J5, finally Vn minus 1 E N minus I J. So here for the convenience, the excitation coefficient is the same. Then A theta radiation pattern can be V0 1 plus EJ5 EJ 2 times this N minus 1 time. This is the addition of the same ratio. The ratio of difference is EJ5. So there is a normal manner to obtain this this sigma value. Then this ratio is multiplied and subtract. Then multiply exponential J5. The first term becomes second term. This is 2. And the final term is N. So if we subtract from this one to this one, then is theta 1 minus, then so only one survive, and this only one and the final survive. Each part can be cancelled. So this is a technique to obtain this summation, to multiply this ratio. So this can be shown like this: a theta 1 minus epsilon j phi equal this is this part. This is 1 and final. So a theta is expressed by this calculation. So this part is exponential is cosine and j sine. This 1 minus j phi also is equal. Yeah. Complex number can be more simply this absolute and the phase. This phase is determined by the ratio of the real part and the imaginary part. Like this, imaginary part divided by the real part will be, if this ratio is tangent side, then it can be expressed by this absolute and this. The lower part also same. So rewrite the a theta become this root. This is this square and this square plus this become 2 times 1 minus cosine and phi. This part become 1 minus cosine phi. And this complex part. So if we consider absolute value, then it becomes this 1 minus cosine is equally square value. So this is 2 times 1 minus cosine is 4 sine square. This lower part also 4 sine square half sine. So finally, a theta can be expressed by this one. So absolute value becomes value. This is the radiation pattern of antenna. So the image of this function like this. This is well-known function. This is a sampling function. So it becomes at upside 0, it becomes n maximum value, and at upside equal 2 pi divided by n, then this value become pi. So this becomes 0. So this is the pattern becomes phi equals 0. Then it becomes n, and this like this. This is the radiation pattern. Depending on psi. However, psi is this function, so we can convert to theta. So at the psi 0, theta becomes half pi, and theta becomes 0. So if this is a rectangular coordinate, if polar at the theta equal a half pi direction, it becomes highest and become like this. This is a radiation pattern. And sometimes the separation of elements is used half wavelength. So in this case, this function becomes more simple. Sine 2 pi cosine theta sine m 2 pi sine theta. This 0 point become 1. So this is express the point position. So we can derive the radiation pattern equation like this by adding all the elements and obtain the summation. It becomes like this. And finally, divided by E0, it becomes pattern. So this is a very famous pattern of sampling function. And next, the main, another important, here we understand the shape of this radiation pattern. So specific value is half power beam width. This half power is from the center to this level is half power, 3 dB down. That width, beam width is called half power beam width. This is important parameter to understand the radiation pattern. The half power beam width and the antenna gain. These two keywords is characterized antenna radiation pattern. So this half power beam width is almost half of this null angle. So null angle of plus part and minus part is satisfied this one. At this point, generally expressed by this one, n pi divided by p cosine equals pi. So this from this finally p divided by lambda n cosine 1. So if this is smaller, then this one angle is 2 pi plus lambda divided by mt, and the minus angle is 2 pi minus. So this separate angle is this one, 2 pi divided by mt. This is so our beam width is half of nu. So it becomes L divided by LD. This is unit is radian. So by express total array length is used lambda divided by total array length. So this is very useful equation. The beam wide sharpness of the beam is expressed by lambda divided by total array length. So the unit is radian. So we understand in degree, then multiply conversion to radian to degree is 180 divided by pi. This number is multiplied to radian that can be converted to degree. So another important characteristics is antenna gain. Antenna gain is using, so we obtain D. So this D is put here. So this is all direction pattern is shown. However, here that is this is only the center value. So this integral is all over the space. All over the space divided by 4 pi is unit angle. So unit angle intensity is used to divide the maximum value. This is the definition of antenna gain. So if we calculate by using f theta equals this function, the calculation is not so easy. However, we can obtain very simple result. G equals 2 times ND divided by wavelength. So this is ND equals antenna total length. So total length divided by some very simple expression obtained for gain. So two important radiation parameters: half power beam width and antenna gain. So from these two expressions, half power width and this antenna gain is inverse relation. So this is the fundamental equation of how to calculate radiation pattern, and this is radiation pattern function. By using this function, we can obtain gain and sharpness of beam. So yeah, the beam direction is fixed case. However, this is a phased array. By changing phase shifter value, we can change the radiation direction. This already I explained in the wireless and mobile case, so you can once more check by yourself how much space should be given to achieve radiation direction. This is duration, this phase shift angle, phase shift value, and this is the radiation direction. By using this equation, to achieve theta direction radiation, the phase shift angle is given. So, considering this equation, if we adjust phase shift value, we determine, we can control the radiation direction. So this function is called phased array antenna. Phased array achieve radiation direction in any direction by this equation. So this is at first this is a mobile base station. Radiation pattern to the radio zone edge is to be very strong. However, from the outside cell, interference should be small. So radiation to the another cell and the inside this area is my own zone. This area is another cell zone. So to achieve this unsymmetric radiation pattern synthesis is achieved. That is performed by adjusting the this excitation coefficient. The relation of excitation coefficient and the achieved radiation pattern can be expressed by this vector equation. This multiply can be expressed by this vector calculation. So that this is the radiation pattern T, and this is the excitation of each element. And this part is exponential jk phi. So this matrix vector equation by this equation, the radiation. So this A is objective, the sampling point of objective. So to achieve, to determine the excitation coefficient, to achieve this one, then the difference of A and F, this is the difference. This is the error function of difference of A and F. To minimize this function, we can calculate the solution. So this method is called least mean square method, LMS. So by this minimum error of A and F, by solving this equation, we can obtain the excitation pattern pretty study determined by the solution. So like this, we can achieve this symmetrical radiation pattern. So not only array antenna is this static radiation pattern, this beam scanning operation and radiation pattern designing. There are many technologies relating to array antenna. So still, for the purpose of application of this antenna, still many design technology is developed. So I would like to finish my lecture. So finally, this is report 4. Answer the next equation. Designer rectangular patch antenna, frequency is 2 GHz and substrate permittivity equals 2. So using this equation, operating at 2 GHz, honeycomb antenna designed by yourself. And next, obtain array antenna gain in dBi and beam with theta in degree. The equation is radian, so convert it to degree. And this is not dBi. So this value should be, gain value should be shown to dBi. Decibel calculation, and this is convert radian to. So frequency is similar, same to 2 GHz, and array length is 3 meters. This is almost the same as the graph